All right. So, if you'll recall, we had a situation at the glass factory. They had some ammonia that they were using, and it was causing some problems with the pond. And we've sort of studied how we could stabilize the pond with our buffers. The last piece of this sort of acid and base stuff we really need to talk about is how do we figure out what concentration solutions are? How do we neutralize? How do we react acids and bases together? We've looked at acids as equilibriums. We've looked at bases as equilibriums. We've looked at a little bit of them together. Back in the day, back in chapter 3 and 4, we talked about acids and bases reacting together, and we did some calculations, some stoichiometry calculations about neutralizing them. What we need to do is we need to combine that with our ability to understand the equilibrium that follows from doing the stoichiometry so that we can really develop a more holistic picture of titration. Titration is a chemical process. It's a laboratory technique where we take one substance, one solution, and we add to that another solution. But we add it in a very careful way, in what we call a volumetric way. That is, we measure very accurately the volume of solutions that we're mixing together. And typically what we're looking for is we're looking for the point where the moles of acid are equal to the moles of base. That's what we call our equivalence point. So the equivalence point is defined as the point at which the moles of acid are equal to the moles of base. We know that we're going to be working with aqueous solutions. For those aqueous solutions, we know that we can calculate the moles by looking at the molarity and the volume. My molarity of acid times the volume of the acid is going to give me the moles of acid. And conversely, the molarity of the base times the volume of the base is going to give me the moles of the base. So, we want a chemical way, we want a laboratory way to find this point. The point at which we have just added enough of one substance so that we have reached that equivalence point. The technical procedure, the laboratory procedure we do, that whole process is called titration. And typically what we do is we use a flask, usually something like an Erlenmeyer flask, and we take one of our substances. Okay? In this case, let's say we have some acetic acid. We want to find out what is the concentration of this ethanoic acetic acid. So we're going to take some of that and we're going to pour it in there, right? So we have some vinegar, we have some ethanoic acid here. What we want to do is we want to react it with some base that we know the concentration of. And there are various ways that we can find the concentration of a solution as we're making it, or afterwards there's a similar process to this, as you'll see next week, where you can take a solution that you don't know and use a solid that we can weigh out very easily. But the idea here is that we're going to take a solution, and to this solution, this ethanoic acid, we're going to drip in some base, probably something like sodium hydroxide. And at some point, the moles of the base that we've added will equal the moles of acid we started with, and we'll be at the equivalence point. We need something in this solution to tell us when we get there. We need what we call an indicator. Indicators are substances that, typically they're weak acids or weak bases, that will react, will change color based on the pH. So we're looking for an indicator that will change color when we're at a pH that is at this equivalence point. And we're going to talk about how we can find that in a few minutes. But the basic procedure is we add the indicator into the solution. Okay? So we add that indicator. It will change color when we have hit this equivalence point. So now we take a solution of sodium hydroxide in what we call a burette. Okay, so this is a burette, and you can see it has a valve down at the bottom here. This valve is called a stopcock, and it allows us to very carefully control the flow of the liquid. So we're going to run some sodium hydroxide out of here down into the acid. Okay? And when that happens, when we hit this equivalence point, the solution will change color. The indicator will change. The indicator that we might use here is called phenolphthalein. Okay? And that phenolphthalein changes from clear to pink when it is in a basic solution. So in a slightly acidic solution or neutral solution, it's clear. When it gets a little bit basic, it changes color to pink. And that's because of it's a weak acid, and when the hydrogen from that indicator, the phenolphthalein, when it loses a hydrogen, the molecule can absorb light and change from clear to pink. So that's the basic idea here. We do a reaction. We're going to mix two solutions, an acid and a base. Typically, we're going to mix a strong something with a weak something. So a strong base, sodium hydroxide, with our weak acid, or a strong acid with a weak base. That's the typical procedure. The key, however, to choosing the indicator is that we have to know what is the pH at the equivalence point. It's not going to be neutral, and we've seen that. Yesterday, we talked about salts. Remember the ionic compounds? Back when we were talking about bases? We had the ions that are left over can change the pH of the solution. So when we've completely reacted these, we're going to have acetate ions in the solution. And those acetate ions are going to affect the pH. So the pH isn't going to be at 7. We're going to have to figure out what the pH is so we can choose an appropriate indicator. We're going to want something that will change color at about that pH. And there's a big list in your textbook. There's a table, full color table, that shows indicators and what color ranges they change, what pH they change color at. So, the basic procedure is nothing new. It is what we've been doing. We are mixing an acid and a base. So we are going to do a stoichiometry problem for assuming we use up all of whatever the strong stuff is. In this case, it's going to be a strong base. Use that all up. Find out what's left. How much acid, how much conjugate, weak acid and its conjugate. How much of each do you have left? Use those as your new starting values for an equilibrium problem. Okay? So these are two-step problems, 2 stages. Stoichiometry first, then equilibrium. So, let's say we're running this experiment. And there's a couple of important points I want to point out along the process of doing this titration. The first sort of one is what we call the halfway point. The halfway point is when we have reacted, used up half of the initial substance we started with. So we started with our weak acid, ethanoic acid. Let's say we had 100 milliliters of 0.5 molar. When we've added 50 milliliters of 0.5 molar sodium hydroxide, we will be at what we call the halfway point. We will have used up half of the acid. And there's a reason why I'm showing you this point. It's an important point, and we're going to see it in a couple of different times. It's also very useful to us for a particular property. So, what's our first step? What do I have to calculate first? What type of problem do I have to do? Not an ice diagram. I have to do a stoichiometry problem. So I want to know how many moles of hydroxide do I have? Right? 0.05 liters times 0.5 moles gives me 0.025 moles of hydroxide. How many moles of acid do I have? Right? 100 milliliters, 0.1 liters times 0.5, 0.05 moles. And I have none, and none. Because I'm at this sort of, I calculate, no matter where I am, I calculate as if the reaction has just happened. Because that makes it easier than trying to do a continual calculation process. That's very difficult to do mathematically. So we always imagine that we just mix these two things, even though that's not actually the process we did. We added it drop by drop, a little bit at a time. But we imagine as if I just poured those two things together, simplifies our math. So, this is a stoichiometry problem. Why is that important? What does that mean? What do I do for this next step? Are there x's involved? What is my assumption? I'm going to use up all of the strong base. So I'm going to assume that I use up all the strong base. It's a 1-to-1 relationship, which means I use up the same amount of acid. How do I know it's a 1-to-1? Once I write the balanced chemical equation, this is a 1-to-1, right? There's no coefficients here. If there were coefficients, I'd have to deal with that.
How do you know the OH is strong?
The example that we've been talking about is sodium hydroxide reacting with ethanoic acid. Sodium hydroxide is a strong base that we have memorized.
So is it just kind of like a coincidence that when you subtract 0.025 from 0.05, that ends up being the halfway point?
It's not a coincidence. I picked this point particularly to illustrate this point. The halfway point is always when you have used up half of what you started with.
Are we doing this to find?
We're doing this so that you'll see what does it look like at the halfway point. How can we identify the halfway point? But we're doing it from the reverse. I'm telling you this is the halfway point. I've set this system up so that we're at the halfway point. Finding the halfway point from doing a titration involves a little bit different process that we'll talk about in a minute. Graphing is going to be helpful to us in that process.
In general, if we had a problem like that, we would just subtract the amount of OH.
Yes, generally all this, it's going to run the same sort of way as you'll see when you start to look at the homework. Calculating the pH of where we are during a titration involves doing a stoichiometry problem and then doing an equilibrium problem. That's the process. So we're going to not care about the water, and we know we're going to produce 0.025 moles of our acetate ions. So I have no hydroxide left, and I have 0.025 moles of the acid and 0.025 moles of the base. What have I formed? At this point, what would we call this solution? What did we learn about yesterday?
Oh, wouldn't that be like a buffer?
Buffers, right? What are buffers? How do we define a buffer?
A solution that can react with either bases or acids.
Solution can react with either acids or bases. Good. What do we have to put in to form a buffer?
You need equal amounts.
Doesn't have to be equal, but you have to have a weak acid or a weak base and its conjugate. So look, what do we have? Here's a weak acid. Here's its conjugate. We have both of these in the solution. We have a buffer. The halfway point is also called the point of maximum buffer capacity, because it's the point at which we have maximized the amount of forward and backwards we can go, the maximum amount of acid or base that the solution could now minimize the change on. A buffer is a solution. It's not a chemical. It's a solution that contains a weak acid and its conjugate. Conjugate is the leftover part after an acid has lost a hydrogen, or the leftover part after a base has gained a hydrogen. Okay? So, what equilibrium is going to govern this mixture? Is this the equilibrium equation I should use? What kind of equilibrium should I use for this problem? Ka, something that represents the Ka value, so which is going to be acid dissociation, which is going to be an acid breaking apart into a hydrogen ion and its conjugate. So I did the stoichiometry. I now have the starting points here. But this starting point is in what units? And to do equilibrium, what units do I have to be in? Concentration. I need to be in molarity. So what do I have to do to these moles to turn them into molarity? I got to divide them by a volume. What volume should I use? The total volume of the solution. That's one of the big tricky parts of a titration. The volume is constantly changing because we're constantly adding more liquid in. We're adding more hydroxide. What the total volume here is going to be 50 plus 100 or 150 milliliters. I need to divide each of these values by 0.15 so that I can calculate the molarity of my values. And again, we reset the clock. We're assuming that this is now the starting point. So we have 0 hydrogen ions. And I calculate the molarity of each of my things. Nope, this is in moles. I took volume times molarity to get moles. Stoichiometry is typically done in moles, and we needed to do that because the volumes are different. And then we have to convert back to molarity here. Now, we know which way this has to shift. Which way does it have to shift? I have 0 hydrogen ions. I have to make more hydrogen ions. So I know that this is going to shift to the right. I'm going to make hydrogen ions, going to make acetate. Now we're back on familiar territory. We can go through. We know how to solve this problem. Is there some shortcut we can take? Yeah, the equation thing. The Henderson-Hasselbalch equation. Henderson-Hasselbalch equation. If you forgot the Henderson-Hasselbalch equation on the test, where could you look it up? On the useful equation sheet. So yeah, 1.8 times 10 to the negative 5 is the Ka value for acetic acid, ethanoic acid. And I believe it's on your handout. Certainly we used it quite a bit yesterday. Yeah, either the information to calculate it or the value will be given if needed. You're not expected to memorize any Ka values. You are expected to memorize Kw. 1.0 times 10 to the negative 14. Actually, I think it's on there. It is on the useful equation sheet. Yep, it's on under the equilibrium section. So now, here's why the halfway point is interesting / important. What's this value right here? What's the log of 1? It's 0. So at the halfway point, the pH is equal to pKa. pKa. In this case, 4.74. So that's what makes the halfway point really useful to us. If we can figure out the halfway point from our experimental data, and there are ways we can do that, then we can figure out what the pKa is, and from that, the Ka value of an acid. Okay? So, knowing the halfway point allows you to figure out the Ka value. If you know the pH at the halfway point, it's equal to the pKa. That's an important technique. It has shown up on tests before, that question. So, this is our halfway point. We've got our pH, okay? The key, pH equals pKa at the halfway point. We're also at our point of maximum buffer capacity. When you have equal concentrations of a weak acid or base and its conjugate, that's the point of maximum buffer capacity. Equal amounts. Questions? All right, let's go on to the heart of the matter. Let's get to that end point, that equivalence point. Okay, remember, again, in the lab, we're going to want to go through and determine this experimentally by looking for an indicator change. But we're going to run through the calculations to sort of simulate what's going on. With the same reaction, okay, same reaction, we have we sort of rewind the clock and say, hey, I had 100 milliliters of 0.5 molar. I would need 100 milliliters of 0.5 molar. So I do the stoichiometry. 0.05, 0.05. Okay? And 0 of this stuff to start with. Who cares about the water? Okay, guys? I'm going to use up all of the hydroxide. That's our basic assumption. Okay? Now, if you had more hydroxide than acid, you obviously couldn't use up all the hydroxide and you'd have some left over. And you just need to watch out for that sort of special situation. And again, what we're going to look for is we're going to look at what's left, and we're going to use that as the basis for our equilibrium calculations. So in this case, instead of adding 50 milliliters, we've added 100 milliliters. 100 milliliters of OH minus is where we reach the equivalence point, where the acid and base are exactly canceling each other out. Okay? So again, we continue. We're going to do our stoichiometry using up all the hydroxide. That's going to use up all of the acid. And we're going to make the conjugate. So what do we have left? We have no hydroxide, no acid, and we have just conjugate. Now, this is the point where we say to ourselves, okay, what equilibrium would be most appropriate for doing this calculation? What do I have in the solution? What would it do in the solution? I've got the conjugate. The conjugate of a weak acid is a base. Now, strong is probably it's not a strong base. It doesn't completely react, but it's a base. Yeah, it's a weak base. So the conjugate of a weak acid is a base. It will function as a base. We should do this as a Kb equation. And Kb is when we have the weak base reacting with water to produce the conjugate acid and hydroxide ions. And this would also be really appropriate if you had excess hydroxide ions, because they could just be a starting value here. Okay, so if you go past the equivalence point, if you add additional hydroxide, you would just put that hydroxide ions as a starting value here. Remember, anything you have at the end of the stoichiometry becomes your initial values for the equilibrium. Do I take this to do it? I got to convert it into molarity. What volume should I use? 200 milliliters, 0.2 liters. I got to remember to convert from moles back into molarity. Okay, guys? Stop. It's concentration. Molarity is a concentration, is a measure of concentration. So, the molarity of the acetate ions is 0.25. The molarity of the acetic acid, ethanoic acid, is 0, and 0 for the hydroxide ions. I have to shift to the right, because I don't have any of these guys. So I'm going to use up acetate ions to make acid and hydroxide. I'm going to do 0.25 minus x. I'm going to have x and x. This is looking really familiar. Okay? Now the key though is I have to use Kb. I wrote a Kb equation. I have to use the Kb value. Ka times Kb equals Kw. So Kw divided by Ka equals Kb. I have that. I've got my x's. How can I make this math not a quadratic? Let's make our 5% rule assumption and say, hey, 0.25 minus x is basically 0.25. So we can make that substitution. We're going to move the 0.25 to the other side, multiply. We can solve for x. What is x in this case? The concentration of hydroxide. Once you get x, you're done with the math for a little bit. You have to really remember your chemistry now. Because this isn't hydrogen ions. You can't just take the pH, can't take the negative log of this and get the pH. Take the negative log of this and you get the POH. Okay? So the POH is 4.9. What would the pH be? Yeah, 9.1. 14 minus POH equals pH. So, calculating the pH during a titration is a stoichiometry problem and then an equilibrium problem. Okay? So, it's not at all unusual for us to be asked to do that, to say, hey, what's the pH at the equivalence point? And then we have to do a stoichiometry problem and then an equilibrium problem. When we go into the lab, however, we're not doing the calculations like this. Typically what we're actually doing is we are, measuring the volume and looking for a color change. There's another way to do it, however, a more instrumental way to sort of look at this kind of stuff. Once we've figured out the pH and we've gone through and we've determined our indicator, that's why we do these calculations, to figure out what indicator should we use. We want an indicator that changes color at about this pH. Now, in the real world, we typically use equipment to help us measure this. We use what we call pH meters, which are devices, what are called ion selective electrodes, that measure the hydrogen ion concentration within a solution. And what we do is we stick a ion selective electrode inside our solution and we measure the pH as we add the base to it. And if we did something like that for this experiment that we were just talking about, that we did a couple of calculations for, we would get a graph that looks something like this. Here is the pH of our 0.5 molar ethanoic acid. Okay? This up here is essentially the pH of our sodium hydroxide solution. You can see the two different points that we talked about. Here is our halfway point. Here is our equivalence point. Couple of things to notice about this. The halfway point is the point of maximum buffer capacity. It's the midpoint of this flat section, this lower flat section. That's the halfway point. And you can usually find it by finding looking for this point here. Okay? Now, of course, we want to be able to determine the equilibrium point. Okay? And we're typically going to do that using graphical methods. If you are given a graph like this, like if on, say, Monday, I do a sample in class, and we collect a bunch of data, and I ask you to do a graph, just saying. What you'll need to do is you will need to go through here and find this equivalence point. Typically, that's done graphically. You take the line up top here, and you extend it. And you take the line down below here, and it's just, you eyeball it as best you can. You extend it. And then you take this line here. It's kind of hard for me at this angle, but. Okay? And you find the halfway point between the half the distance of this line. So this is, 16. That's going to be 8 point something. It's right about there. So my graphical method is a tiny bit off, right? It's an approximation. Plus I'm not working with an appropriate scale and it's hard to do. But that's pretty close. If you think about the difference in volume between those two things, right? Because of the steep slope here, the difference from there to there on the x-axis is really small. And that's why this method works pretty well. You get very, certainly close enough, within 5%, which is the kind of assumptions we're perfectly happily saying is close enough. Okay? And then you could find your halfway point by saying, okay, if the equilibrium, or if the end point is 50, then my halfway point is going to be 25. What's the pH there? That's also my pKa value. Okay? So that's the sort of basic way that we might look at this from an instrumental point of view. Important points, the halfway point, and the equivalence point. And it's the pH at the equivalence point that's going to tell us what indicator to use. Now, one thing we want to point out is we want to look at a bunch of these different graphs, okay, for different Ka values. Because it turns out the strength of the acid has a lot to do with the shape of this line. The weaker the acid, the higher the start point is going to be. So these are 0.1 molar sodium hydroxide added to 0.1 molar acid. Different acids are going to give us different shapes of curves.
Wait, so a
The
lower...
lower the Ka value, right, the higher the starting pH, the more basic the pH, because it's a weak acid, it doesn't break apart very well. Notice that if you think about the halfway point, which is going to be 25 for all of these, this is the maximum buffer capacity. We can get all kinds of different buffered solutions by mixing these together, and the buffered solution is going to depend on the Ka value. All of them have equivalent points, okay, at 50. These are all the same equivalence point, 50 milliliters here. That's the point at which the graph goes really steep, okay? Obviously, the weaker the acid, the less defined that point is. The stronger the acid, the steeper this line becomes, because we go, essentially, we reduce the amount of equilibrium. For a strong acid, there is basically no equilibrium. We go directly from being an acidic solution to just adding a couple of drops and switching to a completely basic solution with just a little amount of base, because it's a complete reaction. It's a complete stoichiometry reaction. They react completely, instead of forming a buffer that flattens this curve out. You can see it starts off and then it flattens out as we form the buffer, and then it gradually goes up as the buffer minimizes the pH change. So the shape of the curve depends on the Ka of the acid. One of the last things we need to think about is we got to understand what happens with different indicators, because choosing the appropriate indicator is an important part of doing this type of laboratory activity to getting a good answer. So here's a graph of two different titrations. This is, see how flat this stays and then sharply goes up? This is a strong acid titration. This is a weak acid titration. And we can see that because of the different starting points and because of the different shapes of these lines. So, here are our example of two different indicators. One, methyl red, and the other indicator, phenolphthalein. If you look at the strong acid, the difference between when the methyl red will start to change color and when the phenolphthalein changes color on the pH scale is quite large. But because of the steepness of this curve, the volume difference between here and here is less than a drop, and very accurate. So if for a strong acid, it really wouldn't matter if you used methyl red or phenolphthalein. For a weak acid, the indicator does make a much larger difference because this curve is not nearly as steep. Methyl red would start changing colors almost right away, okay, and would therefore be a very poor indicator. It doesn't change color around the pH that we're interested in. Our eyes can typically detect 1 part in 10. We need 10% of the indicator to change to begin to detect that color change. So we need the Ka of the indicator to be about 1 less, the pKa of the indicator to be about 1 less than the pH at the equivalence point. So the pKa of our phenolphthalein is about 8, whereas this is changing at about almost 9. So it's like 8, I think it's like 8.8 something. We have to look at that. So here the phenolphthalein is a much better indicator. It changes color, yeah, maybe a little bit after the real equivalence point, but again, volume-wise, that's pretty small versus this difference, that's a big volume difference. So choosing the appropriate indicator depends on what is the pH at the equivalence point. All right? This whole titration process is really about doing it. It's really much more about the actual laboratory stuff that we're going to do. And we're going to do that lab. We're going to do a couple of titrations. We're going to use phenolphthalein indicators. We're going to do this kind of stuff. Figure out what is the concentration of an unknown solution. Okay? But we do that by this process of adding a known base to, in our case, an acid. So in the example was, I have this unknown acid solution. It's ethanoic acid. I don't know its concentration. I'm going to add a known base to it very carefully using an indicator that should change color at about the right point. And look for that color change. Again, we can use this, the Henderson-Hasselbalch equation to look at the pH of the equivalence point. And remember what I was talking about, a 1 in 10? Okay, this is the pKa of our indicator. We need this value to be about 1 in 10 so our eyes can detect it. We want the pKa to equal the pH at the equivalence point plus 1. All right? So we now have the ability to go through and determine how much ethanoic acid. We can dynamically, take a sample and determine its concentration by using a known standard. And we can do that kind of titration problem and calculate what will the pH be at the equivalence point. We're still going to have those acetate ions left in the solution after we do this neutralization, and they're going to cause some problems. We need a way to actually remove those acetate ions completely from the solution if we really want to stabilize this pond. If we want to keep the pH, those acetate ions from changing the pH, we need to remove them from the effluent from the factory. And that's what we'll talk about on Friday.